To proceed, I'd like to talk just a little bit about the last topic of partial correlations, and then spend the rest of our time talking about kind of walking through the homework assignment. So let's come down here. Okay. So far in what we've been talking about, I've been talking about regression, and in regression, sort of depending on the class you may have had, the discussion usually doesn't center too much on the errors of prediction associated with the criterion. And when I teach regression, I talk a little bit about the topics of partial and semi-partial correlations. But in structural equation modeling more generally, we often use the error terms associated with the criterion variable as a way to make a version of the variable adjusted for other variables. So, I mean, some examples of this, if you go over in the before times to Ellis Library, you'd see these rather large social programming substance use posters that say that individuals who drink 5 or more drinks in a sitting also have lower grades. And, you know, actually, one of the things that I've made part of my career about is, you know, that is true, there's a correlation there. But if you adjust for the fact that people low in academic aptitude don't very good grades, and people low in academic aptitude also tend to drink more, that correlation goes down by quite a bit. We can talk a little bit about that, but what I want to draw your attention to are these two path diagrams. And here we have freshman GPA and alcohol, and upstairs we have some predictors of high school class rank. And notice what's happened here. This is, if we look at this as a path diagram, this is a 2 predictor regression for this variable and a 2 predictor regression for this variable. If we ignore one half of this for the moment and just look at this part of the diagram, this is the error term, and notice we're making use of our 2 ways of expressing error term that we talked about earlier. That I'm going to fix the variance of error here to 1, and I'm going to freely estimate this path. This path has, as its interpretation, it is the standard deviation of the error associated with this predictor, this criterion variable. And the reason that I'm doing that is a correlation coefficient is any time that a double-headed arrow joins 2 variables which have unit variance. So the raw correlation between freshman GPA and alcohol quantity frequency is all of the ways that I can travel from this variable to this variable by the tracing rules. So just for rehearsal, let's look at that. Well, I can start out at 0.19, catch the sling, and go forward. That's one way to travel from freshman GPA to alcohol quantity frequency. I can also go backward, I can also go backward on this, take the covariance up here, and ride this over here. Coming over, drawing our attention to this one, I can go backward on this, catch the 1, and go -2.8. Plus, I can go backward on this, catch this sling, and come forward that -0.3. That's all of the covariance or correlation, if I'm dealing with standardized versions, that I can get from here to here. And what's left over is going backward on this arrow, catching this sling, and going forward on that arrow. So this correlation down here is adjusted for, it's what the correlation between GPA and alcohol is, adjusted for verbal ability and prior academic achievement. It's analogous to what would happen if I were to do an experiment. It's an estimate of what would happen if I were able to do an experiment where everybody in my study had exactly the same ACT English and high school class rank scores. This is the correlation I would expect to observe. So this coefficient down here is known as a partial correlation coefficient. I draw your attention to the diagram on the right, which looks very, very similar. It's just that instead of arrows connecting GPA and high school class rank to freshman GPA, sorry, ACT English and high school class rank, I have double-headed arrows. So what this is doing is I'm trying to assess the relationship between freshman GPA and alcohol quantity frequency, but I am adjusting alcohol quantity frequency for ACT English and high school class rank, and I'm not doing any adjustment to cumulative freshman GPA. Why might you do that? Well, so in terms of words, this is a semi-partial correlation. Why might you do that? Well, I might be interested in knowing if this variable provides any unique association with the criterion after adjusting this variable for these two things. In that respect, the statistical significance of this semi-partial is, the idea of it is exactly the same as you would think about in a regression model, because of the statistical significance of a regression coefficient answers the question, does this coefficient give me anything unique above and beyond the other predictors? Well, you might wonder, gee, what's the difference? In terms of statistical significance, the good news is there is no difference between this semi-partial correlation and a regression weight. And that is why some packages like SAS and SPSS have as some of their options being able to produce semi-partial correlations in addition to regression weights. Generally speaking, in this class, we're going to be using the partial correlation more than we'll use the semi-partial correlation, but I presented in the interests of completeness. So that's the end of that discussion of third variable explanations. We use the term third variable to say I'm looking at a relationship between two variables, and these variables up here are known as third variables, or other confounders is another word that sometimes people will use, that underlie the raw correlation in the data. Right, any questions on that? Okay, hearing none, let's go back now and take a look at the homework assignment. So I'm assuming you're all seeing it, are you? If not, give a yell. So what I was thinking, sometimes when you're proposing your master's thesis or your dissertation, you might be saying, well, I've got to go before my committee and talk about statistical power. Sometimes I might even be interested in simulating some data so I can get my structural equation modeling program to work before I collect the data. So I was thinking, let's look at that. And what I set the task before us is to think about your own research area and think about a two-predictor regression model. The two predictors can be anything you want, and the criterion can be anything you want. And anytime I do a new assignment like this, I've learned that it helps to walk through an example. And in this particular case, your mileage will vary. You'll pick different correlations, different regression weights, but this is how I would do it if I were in the class doing an assignment. In my example, I've done a lot of work in how college students change, from freshman year to people like you to people who are about to defend their dissertations. And the construct that I'm interested in is something called reflective judgment, which is an interview measure. I can gab all day about that. But for the moment, One thing people have said in the area is, well, reflective judgment is just your verbal ability, and maybe it's already measured by tests that measure things called critical thinking. So in this example, I'm going to look at critical thinking and verbal aptitude and how those are related to reflective judgment. And I might think about, off the bat, a plausible value for a correlation coefficient. Just for the heck of it, maybe those two measures are correlated 0.5. And so I made a little spreadsheet. Well, okay, I've got two predictors. Maybe those correlations are 0.5 with each other. And now let's think about, maybe in my study, what might be some reasonable values for a standardized regression weights. And I'm going to use those standardized regression weights to figure out what proportion of variance is explained by the two predictors. So guessing, maybe 0.6 is the regression weight for critical thinking and 0.4 is the verbal ability one. So looking at this, I made a little space on the spreadsheet, and I said, well, here's my first regression weight, my second regression weight, and I put some numbers in. Now, one of my goals for you is, impress your advisor and your research team with your skills. You'll notice you have little Greek letters in that spreadsheet there. You too can put Greek letters in material. So you come up here and you enter the text, and when you'd like, you highlight that letter, and then upstairs here you type in the name of the font, the symbol font, and that will give you Greek letters. Well, over here, I'm calculating the R-square for the model. Well, by the tracing rules, if we go back to the handout, the R-square for the model is going to be D2, this one, squared plus B2 squared plus 2 times this number times this number times the correlation. And all of that is going to give me the R-square for the model. And the reason it's kind of fun to do this inside of Excel is you can go in and you can play around with these cells and experiment. So notice, for example, if I enter 0.8 here, whoops, now my R-square goes up to 0.904. It's also a check on whether my values can be reasonable. So if I say 0.7 here, there is no world in which the correlation between my two predictors is 0.8 and my standardized coefficient is 0.7, because that would give me a squared multiple correlation bigger than 1. Okay. Well, once I have the R-square for the model, I can calculate what the error variance, the proportion of error variance is by taking 1 minus R-square, and that would be 0.2. Well, that's good. So let's come back to this. Now, the next thing is to think about maybe what the covariance is between the two predictors. Well, in order to answer that question, I need to make some guesses about what the variance of the two predictor variables are. Just for the purposes of an example, 0.4 and 0.9 might be my two variances. So if you look at equation 3.15, that gives you the formula for a covariance. Specifically, that's the correlation times the standard deviation of the two numbers. That's why I actually picked 4 and 9, because I can take square roots of 4 and 9 fairly nicely. Well, in terms of my spreadsheet, I can make a variance-covariance matrix here and put a 4 here and a 9 here, because in a variance-covariance matrix, the variances sit on the diagonal of my predictors. And then over here, I can type in that that's going to be whatever my correlation is, B2 in this example, times the square root of what's on the diagonal, A6 and B7. All right, well, let's come back to, now I've got the covariance and I've got the variances of my predictors, and I need to figure out what the unstandardized regression weights for my model should be. Well, in the handout, 3.2 tells you the formula for an unstandardized regression weight given a standardized regression weight. And I joked about that. Whenever you want to think about how to go from an unstandardized to a standardized regression weight, you always remember that term beta B sexy. Beta, the standardized regression weight, is equal to B, the unstandardized regression weight, times the standard deviation of X divided by the standard deviation of Y. So in this case, I'm going to come back into my spreadsheet and say, well, maybe the variance of my variable is, of my criterion variable is 16, mainly because I can take the square root of 16 rather nicely. Well, if that's the case, then the unstandardized regression weight is going to be the standardized regression weight, in this case 0.6, times the standard deviation of Y, that's the square root of this, divided by the standard deviation of X, the square root of that could be 1.2. And the same thing's true for the other one. The second unstandardized regression weight is going to be the standardized regression weight times the standard deviation of Y divided by the standard deviation of X. The error variance of Y is going to be the variance of Y multiplied by the proportion of variance. Well, now I'm in a stage where I can now draw a path diagram that corresponds to all of the unstandardized coefficients. So we go into Onyx, and we're going to make a new empty model. I'm going to move that to here in the middle. And I'm going to start drawing things. So I'm going to make an observed variable here for the purposes of keeping things straight for me. Let's call that the critical thinking measure. And over here, it's ACT, okay. And over here, we'll make a variable, and we'll call that ACT. Well, the variance of critical thinking and the variance of ACT were chosen to be 4 and 9, respectively. So I can come in here and I can put the number 4. I can come over here and I can put in the number 9. Now I want to join these two with a sling. So I hit Shift, connect one box to the other. I can free that parameter, and the value that I want to put in is going to be 3. I got that from the spreadsheet. Okay. Now I'm going to add in my criterion variable. That's going to be reflective judgment. And I will join that criterion with these two regression weights. These two regression weights are going to be 1.2 and 0.53. I'm going to free that, by the way. And that, and we'll make that. 3.53. And downstairs, I need to specify the error term. The error term is going to be 3.84. So there you have an implicit means model. I haven't made any decisions about what the means of the variables are because maybe I'm only interested in the statistical significance and the properties of my data in deviation score form. Now comes the fun part. Because I've specified the structural model, I can right-click on this and come down here and select the Simulation tab. And you'll notice that it says I can simulate 100 rows of data, and I can also specify the proportion of missing data. And that's kind of handy if you're doing your study and you know you're not going to get complete data. You can put in a number there, and you can say, well, what will my data look like if I have only half of it, say that's not missing. So let's start the simulation. And it has now created for me a simulated data set for this model. And you'll notice that the mean is pretty darn close to 0. And there's no missing data and so forth. And this is what the properties are. Well, I can save this data set. To data, for example. And I can now send this data to the model. And this will now analyze this particular data set for me. So I can come down and look at the estimate summary. And I will see that, yes, indeed, it is running the model and giving me estimates and standard errors. So let's now look at the power of this model. In the handout, in the chapter, I talked about the wall test, that is the parameter estimate divided by its standard error, and we talked about how that denominator is n-1. There's another way to compare models within structural models known as the likelihood ratio test. In the likelihood ratio test, I run my model once the way you see it, and then I run my model again, setting one of the parameters to be 0. And then I compare the relative fit of those two models. So to do that, let's give this model a name. Let's call it full model. And if I right-click up here, I will see an option underneath Edit, which says Clone Model. And what that's going to do is to make a copy of my picture. Ta-da! So here now we have a model which is exactly the same as what I had before. And let me give that model a name, ACT null, because it's going to be the model in which this regression weight is fixed at 0. Well, let's fix this parameter, and specifically, let's fix this parameter to the number 0. And I can now send my data to the ACT null model, and the computer program is going to be running both of these models. And what I want to do now is to compare the fit of my full model, where this is a free parameter, to this restricted model, where this model has been fixed to a value of 0. And to do that, I hold down the Shift button, click on this model, and drag it over to this model. And you will see there's a little black dot that happens in the middle. Hovering over this little black dot will give me a likelihood ratio test of 45 with 1 degree of freedom and a p-value of 0. So by the likelihood ratio test, this model is saying this model fits better than this model. I can similarly test the other model as well, that is the null hypothesis associated with critical thinking. So I can, again, go into Edit, clone the model, drag that down here, maybe name it just to keep things tidy. CT, no. Hold down the Shift key, go from one model to the other. That then allows me to hover over this model, and that model is also statistically significant. Oh, wait a minute, I've got to fix this to 0. Apologies. There. Okay, now when I hover over it, I'll have a degree of freedom and it's statistically significant. So that's a way in which you can compare the likelihood of two models. Now, in your life, at this stage with your skill set, you might be doing regressions and they might have missing data in them. This is a way in which you can compare nested regression models in the presence of missing data, doing what is called full information maximum likelihood. So are there any questions?
I have a question, Professor.
Good.
Yeah, so in this case, it seems that you are not starting by any existing data set, but that you are creating a simulated data set, is it?
Yes.
So how do you get this correlation matrix without any, like, based on assumption?
Well, so if we go back to our little spreadsheet, we can look at the numbers that we have. We had to make them up. So usually what you're doing is you're going back to previous studies and you're saying, you know, other researchers have found a correlation between ACT and critical thinking, and this is what it's like. When you're doing a grant application for like the National Institutes of Health, you need to select plausible values. That's usually done by a review of the literature. There are some folks who refer to books by Jacob Cohen for small, medium, and large effect sizes. And those help to steer what your choices for the standardized regression weights would be. To some extent, you know, if you have a lot of worries about, you know, you don't really know what the variances of the variables are, then don't worry about it. You can run the model and say, you know, the variances of all of my variables are 1, and the reason I'm doing the analysis is to explore a variety of effect sizes.
Clarify the correlation and the variance are based on the studies, previous studies.
Yeah. I mean, you can do that. I mean, that's what I do. Often in a lot of areas of social psychology, maybe it's not your particular instrument, but there are other instruments like it that you can get a general idea.
And for the homework, could we do like that, the procedure, or what if we find any that to?
I'm sorry, you faded out. What if we don't find any? What?
So for this homework, are you prefer us to do this kind of procedure, like find out the existing studies for the correlation and variance?
Oh, you can do whatever you would like. As a matter of fact, if you don't want to look at any studies at all, and you just want the exercise, find some numbers and make them up. I'm just saying that, you know, what makes it useful to you, if you are on the verge of doing your own regression analysis, you might want to look around at things in your area. But if you don't just want to say, oh, I'm interested in making some numbers, maybe the correlation between the predictors is negative, you know, just this gives you an opportunity to use the equations in the chapter and do something that might be professionally interesting to you.
Okay, thank you.
All right. More things? Was I transmitting the whole time? It was really quiet. You can come back here, by the way, and show the standardized estimate and see how closely you get to the known coefficients that you actually had when you made the data. Those types of things.
Another question, Professor.
Okay.
So what you show us is the summary or the descriptive statistic, but can Onyx produce the data set as well that we can see?
Yes. Mm-hmm. This is what I did when I saved this, is that made a data set that saved it. Let's go into here's the data set that was created. It should be coming up. There it is. So I might have to use the text to columns thing to bring it down here, but nope, there's the data. Those are the numbers. So you can take that data set if you wished and read it into R and analyze it there, or SPSS or SAS or anything. So now let's do something a little different. Let's ask ourselves the question, if there's a partial correlation between two of the variables adjusted for a third variable. This is an example of using the diagram that we saw before. Well, let's come in and create an empty model. And let's drag our measures into it. And perhaps verbal ability is a general measure. And I want to know if there's an association between critical thinking and reflective judgment after adjusting both of those variables for that. All right, well, to do that, I'm going to have to make ACT a predictor of critical thinking and ACT a predictor of reflective judgment. And now I need to make error variances that have a variance of 1. Well, to do that, I'm going to come in here and delete these slings and add a latent variable. And I want to fix that value to 1. And I'm going to add another latent variable over here. And I'm going to fix its value to 1. And I'm going to make a regression weight here, and a regression weight here. Free these values so that they are the error standard deviations. And draw a covariance between these two error terms. And free it. And that now gives me an estimate of the partial correlation between the critical thinking and reflective judgment, adjusting both of those for the effects of ACT. So if, for example, critical ACT was a third variable explanation of the association between critical thinking and reflective judgment, I would see a 0 correlation here. Seeing that the correlation remains means that the reason that critical thinking and reflective judgment are correlated is not due entirely to just ACT. Okay. So that's another thing you can do in the homework. And finally, let's come back and draw a factor model. Well, again, here's our data. And we'll drag that over here. And I want to add a latent variable to this. I'm going to fix this at the number 1 and draw paths from that latent variable to all of these. And there, I have done a factor analysis. And we'll obviously in subsequent chapters talk more about what a factor analysis means. And if you would like, we can also look at the standardized coefficients that correspond to that factor model. But conceptually, what I want you to understand is that there's a latent variable out there, and a factor model is saying that this latent variable, whatever it is the third variable explanation, accounting for all of the relationships between these manifest variables just the same way as, in this case, a zero covariance between two manifest variables means that another manifest variable is a third variable association for all of the relationships between two other variables. Now I see in this model that, I've got a standardized coefficient bigger than 1 and I have a negative variance down there. So for this particular example, this is not what we would call a proper solution, but the point of the exercise is here's a diagram and here's what it looks like. We'll get more into improper solutions when we talk about that later. Okay, any questions on that?
I think I have a question.
Okay.
In the model prior to this factor model, where
Yes.
ACT was the predictor for critical thinking, and so should we worry about any potential feedback effect of, say, critical thinking on ACT? Like, does this model capture that?
Right, it does not account for that. And when a person writes up a discussion section, that should be a limitation because we didn't gather data that would allow us to assess that reciprocal effect. That's a great question. It's possible to do a study where we could do that, but in this cross-sectional study, with the variables we have, we can't do that. It's agnostic. So I'm hoping that there are the instructional supports, that this motivates a little bit of navigating back into that chapter and playing around with Onyx and having a data set that of your own design that's interesting to you that allows you to play with things. And if it doesn't work, let me know. We have the weekend now for you to sit down and work with it, and you'll have a sense of whether this is hard or easy for you. And I'll try to push this video out fairly quickly so that you've got that to look at. Any other things about this? Well, we have a few minutes left. Let's turn back to the handout and talk a bit about that factor model. If you have the mean in the model, we're just estimating those means explicitly. The means are kind of arbitrary things. The means are only going to mean that the rest of my diagram is a statement about variances and covariances. To provide some fun clues for what's going to happen later, if I start to estimate the mean of my latent variable and get rid of these intercepts down here, I'm doing something called a growth model. But we'll get to that all in good time. If I standardize my model, this is what a factor model looks like. And these are proportions of variance accounted for. So notice that a factor analysis model looks very much like a single regression predictor model. It's just that, oops, I forgot to have a predictor variable. It's not a manifest variable, it's a latent variable. But I can calculate the proportion of variance of this manifest variable the same way as I would in regression. It's 0.71 times 1 times 0.71. And that number plus 0.49 gives me the number 1. So if this is a standardized solution, that means the variance of that variable is 1. The same thing applies to the other ones. Minus 0.53 times 1 times minus 0.53 plus 0.71 gives me the number 1. The correlation between this variable and this variable is 0.71 times 1 times minus 0.53. So is that good? Yes.
Yeah, so just wondering, so for this factor analysis, the diagram seems to me that the latent variable explain this 3 manifest variable. We interpret like that?
Yes.
So if it's so, then because previously we make a model where the C is explained by T and D, and now we have latent variable explain these 3 variables.
Yes.
So does it mean that in our previous model where C is explained by T and D, there is a spurious relation?
Well, that's a good question. So let's walk down that road a little bit. Remember, in the past, I told you that a regression model or analysis of variance model has as many parameters in it as you have elements of the variance covariance matrix. So in the case of 3 variables, I have 3 variances and 3 covariances, or 6 parameters. And in this factor model, I have 1, 2, 3, 4, 5, 6 parameters. So it is also a just identified model. It perfectly explains the variances and covariances in the data, just the same way as a 2-predictor regression did. So as a structural equation model, they are equivalent, and they're not parsimonious, by the way. They have as many parameters as you have elements of the variance covariance matrix. There is no way to judge whether one should be doing a regression model or whether one should be doing a factor model. They're both just as good. The other thing about it that I like to return to on occasion that seems to be neglected in the books in the area is what is called the naming problem. What is this latent variable up here? Do we necessarily think that it is a platonic, idealized reality of attitudes towards smoking or attitudes and behaviors towards smoking? I don't know. It could be anything. If it's the case that men happen to smoke more than women, that circle could just be sex. And if I didn't have sex in the model, I can't answer that question. So this circle could be one manifest variable or some manifest variables and some other latent constructs. But at the moment, with only 3 indicators, I can't answer that question. With only 3 indicators, and I don't have any of those other squares that might be interesting.
So how could you answer that question without controlling for every possible alternative explanation?
Yes. Well, that's why I write, really good discussion sections of limitations. It has to deal with your philosophy of science. At the end of the day, you can say, I can defend my model against some other models, but I can't defend them against all models. Nonetheless, what I have done is a useful contribution relative to what we knew starting out the study. But, it really sticks in my daughter's brain that, if you were an evil scientist, what you need to do, and you wanted to make some outrageous claim like, oh, I don't know, say, women are stupid. Well, so you have a whole bunch of manifest variables out there. I don't know, pick a number of stereotypes that maybe are things that only men know about that women would be less inclined to know about. If you gave that out as a questionnaire, those would have high correlations, mainly because men respond differently to them than women. And you could do a factor analysis and the fit would be wonderful. And you'd have your latent variable of intelligence based on these biased items. But if you never include sex in the model, it's going to have very high loadings. It's going to fit very well. It'll be very reliable. And then after that, you could say, well, now I have my latent variable. Let's do a multi-group analysis. Well, at that point, yes, women are going to score differently than men. But you have not made it true just by doing that analysis. At the very beginning, you should be thinking of confounds for your data. And in my case, for example, people are in a rush to say, alcohol is the road to ruin, and look at this correlation between how alcohol is related to grades. Well, dumb people drink, and we should take into account the fact that people do not come to us in college alcohol naive, and they make poor choices if there happen to be lower in verbal ability. So you're right, you can't know. Structural modeling is a way of saying exactly how much you can't know, so that makes it good. But there are some types of counter arguments, like those reciprocal causation issue. You can only answer with longitudinal data or possibly maybe genetic data. But as it stands, we kind of know how bad our models are. That's a good educational goal for a class in statistics.
If you do have longitudinal data, would you then put that reciprocal relationship in the model?
Well, it depends on the type of longitudinal data you have. If I have P-technique data, sex is not an alternate explanation for the associations because your sex does not change. If I have longitudinal data, I can also address the question of how data changes over the course of time. And I can also start answering some questions about whether the correlations that I observe are the same correlations for different classes of people. So, I can do more things with longitudinal data, as we'll get into later in the class when we get into longitudinal data. But, cross-sectionally, one of the nicest images I ever saw in a statistics book was Raymond Cattell talking about a boat on the ocean. And he said, well, with cross-sectional data, it's like a painting. You can see the waves, you can see the ship, you can see a mountain in the background, but you have no idea what's going to change about that picture. And by contrast, if you have a movie, you can see, oh, these waves are relatively temporary phenomena, and the boat is moving from left to right, and the mountain is staying the same in the picture. And you can know more mathematically about what is a trait and what is a state and what is inter-individual difference and what is intra-individual difference as a result. It's incredibly nerdy to talk about imagery you found in a statistics book. That was fun, but that's what I am. Okay. I see we're at time. Feel free to ask any more questions. I have office hours afterward.